Few more. I have just letting a few of the derivatives get complicated so I can review while we're going through these. So the first derivative, right, we have 2t, and I'm going to write it up here. Actually, this is what I was going to do earlier. This is a great habit I want you to get into, especially as we go forward, is I actually like to label each component and then just write down what my derivative is going to be. I know it seems silly, but it's going to make simplifying these things a lot easier. So f of t is 2t to the 1/2. G of t is negative 2 over t. And we can go ahead and let's change that to negative 2t to the negative 1. And then h of t is ln of t. Now let's take our derivatives. F prime of t. Right, the half comes down, cancels with that, and then we get t to the negative 1/2. So I got 1 over the square root of t. G prime is negative 1 comes down, makes it a positive 2. Then it's t to the negative 2. Okay, that's 2 over t squared. And then this one that comes up a lot, derivative of ln of t is 1 over t. Okay, so now we have that. Let's go ahead and grab our second derivatives as well, and then we can just write it all down at once. Okay, I like using this definition better. I got negative 1/2 t to the negative 3/2. So that is a negative 1 over 2 t to the 3 over 2. Then g double prime of t is negative 4 t to the negative 3, which is negative 4 over t to the third. This one, okay, this one comes up a lot. I would start memorizing this one, or being able to think about it in our heads. If it was a t to the negative 1, it'd become negative, and then it would go back down with a 2, because it would go down 1. So that's what we get for that one. All right, then I just write out my answer. What this does is everything's nice and pretty. I didn't have to try to keep order of taking a derivative of the I component, doing another and J and K all at the same time, and then showing multiple steps that way. This way I can just kind of keep it all in line. And once our derivatives become more complicated, this will make it easier to do the product rule and quotient rule and stuff like that. Okay, so r prime of t, that is that middle column. It's 1 over the root t I plus 2 over t squared j plus 1 over tk. And then we can write down our double derivative here, which is going to be negative 1 over 2 t to the 3 over 2 I minus 4 over t to the third j, and then minus 1 over t squared k. Not the prettiest of answers, but we did what they asked. I really recommend writing it out like this. I didn't do this actually the first couple times I was teaching this course, and I actually made quite a bit of mistakes just trying to manage all the derivatives and stay clear. I don't remember what I did back when I took Calc 3, but I just know that laying it out this way has made it easier for a lot of people. So my recommendation is to write it out component-wise. All right, so the next one just says find the first derivative, because the second derivative would take quite a bit more work. So we're going to name each component. F of t is negative e to the negative t sine t. And I'm going to go ahead and do my derivative here because I don't know how crazy it's going to get. This is a product rule. Derivative of negative e to the negative t, right? That's going to be e to the negative t, because that negative would make a negative 1 and cancel. So sine of t, that's the first one. Plus I leave the first alone. And derivative of sine is cosine of t. Now we're going to want to get in the habit, and you're going to see this later, this chapter, why we want to do this. But I want to take out this e to the negative t and then write down what's left. So notice I just factored the e to the negative t out. Okay, they just wanted first derivative, so I can end there with the first derivative of the first component. All right. Second component is the inverse tangent. This one's going to start coming up quite a bit. So on the test, I'm going to attach in a table of derivatives and integrals just to, because that's not the most important part for this chapter. It's more of like the content of working with vectors. So you will have a table. I would recommend getting it memorized because I know this integral shows up a whole lot in later this semester, and then it also shows up in DE quite a bit. So G prime of t, if you don't remember, this is 1 over 1 plus t squared. So there's my G. H of t, which is the last one, is negative e to the negative t cosine of t. All right, that gets us H prime. That's what we're looking for. Okay, so this is very similar to earlier we have a product rule. So I have derivative of the first one's going to give me an e to the negative t, keep the cosine. I keep the negative e to the negative t, and I take the derivative of the cosine, which is going to be a negative sign. So that makes a positive term here with a positive sign. Notice both of these have an e to the negative t. Like I said, it does look nicer, but there's a reason later why we want to do this. It has to do with magnitudes. So, because once we start taking magnitudes of derivatives and stuff, and they look like this, having this e to the negative t out front makes it really easy just to pull straight out of the magnitude. So we'll see that when you guys get there. Now we can write r prime of t, which is going to be e to the negative t sine t minus cosine t I plus 1 over 1 plus t squared j plus e to the negative t cosine t plus sine t j. Now, if they asked us to evaluate something, r prime of 8, I would plug in an 8, and that would give me a tangent vector. Remember, that's what we're trying to find through all this is a vector that is tangent at that point. All right, so now we're going to work through an example talking about a vector value function, and we're going to graph it, and we're going to plot something called the point of tangency. You could probably guess what that means. This is the point on the curve that is has that tangent vector. So we're going to find also the tangent vector at this B. Now, don't let this B trip you up. They're going to do stuff like this in exercises on homework and in stuff online. It just means a value of t. All right, so I'm going to write out a couple steps here to help us work through this problem. All right, so the first step is sketch. All right, we're going to sketch like we did in that last section. Okay, x equals 2 cosine t, y equals sine t. Okay, I'm going to solve for cosine t on this problem. Cosine t equals x over 2. Now we can relate those two things together by using the Pythagorean identity. Right, I know that those two things added together squared gets me 1. So plugging this in, I get x squared over 4. That's just squaring it. Plus, okay, that's just y squared, and I'm going to put it over 1 because I like the way that looks. Over 1. That is a y, by the way. A y. This is an ellipse. So here's my graph. I'm going to plot that. And remember when we're doing these, it being a vector value function, we don't know what part of the curve is going to fit under the t that they gave us. So when I plot this, yes, I'm going to be doing an ellipse, but I'm going to do it with the dotted line because I don't know what the curve looks like. I just know it's going to be on top of this ellipse. Okay, so in the x direction, I have 2, and then in the y direction, I have 1. All right, small ellipse there. All right, let's put a dotted line because, like I said, we don't know what part of this ellipse. You got a dimple there on the top right, but it works. Okay, so we have some ellipse like that. I'll fix it once we fill it in. And we have to find where this starts. All right, so let's try t equals 0. If I plug that into R, cosine of 0 is 1, so we get 2, 0. Okay, so I know it starts here at 2, 0, and let's see where it goes next. We'll do one that makes sense with the trig functions. Let's do pi over 2. So R of pi over 2, cosine of pi over 2 is a 0, and then a sine of pi over 2 is 1. So it goes up to here. So we know it goes through here. And we know it's going to take how long for cosine and sine to repeat all the way through. It'll take all the way to 2 pi, and that makes it go all the way around. So I know it's this whole curve. So I'll fill it in best you can. All right. And then we have to write the orientation. Well, we just marked it. It goes that way. So I'm going to put those actually in different places because I'm going to draw here. Oops. All right. So we have this ellipse here. And we know it goes this way. There we go. Okay. The reason I did that is now we're going to do the point of tangency thing. We're going to plug in the value wanted. So pi over 3. So we'll plug in t, and we'll flip it to the t instead of the weird b. T to pi over 3, we'll plug that into r of t. So we plug that in. And remember, this is going to get us not a point. It gives us a vector. But we can change it to a point because that's where it's going to be pointing and the curve is going to be at. So I plug that in. I plug in pi over 3. Okay, cosine of pi over 3. Cosine, that'd be 1/2 there, so we get a 1, because 1/2 times 2. And then sine of pi over 3 is radical 3 over 2. Right. Okay, so radical 3 over 2. Perfect. Okay, so this is the point. 1 radical 3 over 2. All right, so we know that's like right in here somewhere. All right, so that's our point of tangency is 1 radical 3 over 2. Right, and then the third thing they wanted was the tangent vector. So what we're looking for here, let's talk a little more about it to make sure we're on the right page. The vector here that would determine that point would look something like that. What we're looking at now is a tangent vector, so it's going to be that looks horrible, but it's tangent off of our ellipse here. You guys get the point, but it's a tangent vector going off that way, so we want to find that vector. So how we do that is r prime gives us our tangent vector. So if we take our derivatives, okay, it was 2 cosine, so that's going to be negative 2 sine t, comma, and then the derivative of sine is cosine t. So that's what we get here. But they don't care about that's in general, at any t. They want it at pi over 3. Or I want it because I wrote it. Plugging that in, so sine of pi over 3 is radical 3 over 2. That leaves us with a negative rad 3. Cosine of pi over 3 is 1/2. This is our tangent vector. It also, because it's pointing, it gives orientation. So you can tell which way the curve is going next. This is pretty typical of our tangent lines and the way we think about them. It's giving us the direction of that point. So, of course, with a tangent vector gives a direction. It actually will tell the direction of the orientation. So if we didn't want to plug in like we did here and figure that out, we could just have done it from that point, pi over 3, and then checked out this and which way it was pointing. It would have told us the orientation of the spinning. All right, let's check out another example. This example, we're going to have a tangent vector, and we just want to find the tangent vector at that point. All right, so we have this. Let's figure out how to graph this thing. We have x equals e to the 3t and y equals e to the negative t. What we want to do is figure out a way to plug these into each other. So what I'm going to do is I'm going to take y, and this is going to feel weird, but I'm going to make a 3t happen inside here. And what I'm going to do is we want to manipulate it to be back to this. So what I'm going to put out here is I need a negative 1/3. So notice if I multiply that back, it gets back to that. But now, since I manipulated it, because I didn't change it, I just made it where if I multiply back, I get back to the original problem I had, I can now replace e to the 3t with x. I forced that substitution to happen. This is y equals 1 over the third root of x. Okay, the third root of x is going to, we're going to have some graph, and we only care about after time equals 0, right? Time being only giving us positive values of x because x is e to the 3t. I can't get a negative out of that anyway. So let's let this be a 1 and a 1 here, and we'll see in a moment what we're graphing. Let's find our point of tangency. So point of tangency, that works. Point of tangency, we just have to find the beginning point, which was 0, of our vector. So plugging that in, we'd have 1, 1, which tells me my point of tangency is 1, 1. Remember, the vector valued function spits out a vector that points at the point. So if I have 1, 1, that's right here. This curve, if you remember, looks something like this, like the rational function. Has that kind of feel to it. So how this vector value function works, though, if we think about this vector, this is pointing from the origin out to that point. That's how it came up with that point. So there's my vector, and then they want us to find the tangent vector. So let's do this in green, and then I'll graph it in green too. Tangent vector. This will tell us the orientation of our graph that's there. How I find a tangent vector is just, it's r prime of t. So r prime of t for this, there we go, I have x and y. We get 3e to 3t. And then the other one will be negative e to the negative t. So those are chain rules, right, for that e to the t function. We want to know where is this tangent vector at time 0. Well, we get 3 there, and then negative 1 there. So what that tells me is from this point, if I go 3 to the right and down 1, which would look something, let's try to make it as nice as we can. It goes off that way, some direction. I know that's not accurate spacing, but I know it goes down that way, which gives me an orientation to my original graph as well. I know that it goes that way. So the answers here, they said find the tangent vector of that function at the point. It's right here. That's the actual vector at that point. The answer here is a generic answer if I want to know any time t bigger than 0. All right, with tangent vectors, we could also talk about unit tangent vectors. If I want to find a tangent vector, which is r prime of t, and I want to make it a unit vector, I divide by its magnitude. So this is a unit tangent vector. All right, so let's find a few things here. It says find the unit tangent vector and point of tangency. Let's do point of tangency first. So point tangency. We just plug that value into our function. So we have r of pi over 6. That's negative 2. Okay, so pi over 6. Pi over 6 is my lower triangle. Y is its sign, so it's a smaller value. It's a 1/2, so I'm going to get a negative 1. cosine is the longer side, so that's a radical 3 over 2, so we get 3 radical 3 over 2. And then the last value is just a 3. There's nothing to plug in. So this gives me my point. Remember, that's the vector pointing at my point, but the point of tangency is negative 1, 3, radical 3, 2, 3. So there's point of tangency. The unit tangent vector, let's do that. Remember, that is just r prime. So we're going to take the derivative of each one. I still think it's a benefit to write out your functions. All right, the derivative of that. Oh, I keep putting x. Tons of habits to break when it comes to these sections. F prime of t. All right, that gets me negative 2 cosine of t. We don't get a sign change there. G of t, the y one, is 3 cosine t. The derivative of that gets a sign change, so we get negative 3 sine of t. And then the last function is a 3, so the derivative of that is 0. Okay, so that means r prime of t is equal to negative 2 cosine t I plus. I always put pluses here. I never put the minus in between. I've made too many mistakes over my years putting a minus in between. So if I can avoid it, I do it. If I'm going to write an answer, I'll put a minus, but if I'm going to do more work, I usually change it to a plus. I didn't mean to put a t out there. Should be a j. And then we have plus 0, so we can just drop it. So r prime of, and they wanted it at this certain value, which is pi over 6. iPad's almost dying there. So I don't actually, there's no reason for me to find a magnitude yet until I actually have my vector. I could do it from here and do algebraically and have a formula for it, but I'm only going to plug one value in. So I like to plug it in at this point. So plugging in pi over 6, cosine of pi over 6 is radical 3 over 2, so it's going to be negative radical 3. Plugging a pi over 6 into sine, that gets me a 1/2, so I get a negative 3 over 2. And now I find my magnitude. And I just go ahead and put pi over 6 in there. So that is the square root of those squares. So we get a 3 plus 9 over 4. That works out to be a square root of 21 over 2. I'll let you figure that out, how it gets to that. So now I can actually find my unit tangent vector. We don't put a unit triangle here. There's a reason coming up. You'll see why. We have two other values that look like that. It's a pretty cool application of this stuff. All right, so finding that, I just divide. So we get the vector divided by 21, radical 21 over 2. So this is 2 over rad 21. And I know a lot of you guys are extremely used to rationalizing. I don't care. If you want to rationalize that, you can, if it makes you feel more comfortable because you've had to do it thus far. But at this point, it really doesn't matter. That's an out-of-date practice anyway. It came about, I think, because of the slide rule. If you don't know what that is, it's a nice Google. But I'm not going to make you rationalize. I wouldn't do it in case you make a mistake, because then I have to find some way to take off if you make some really tiny mistake. Now, would I count a lot off? Definitely not. It'd be very, very little. But it's better just not to try to rationalize it and just leave it. Okay, so there's that one. Let's talk about tangent lines. How to make one. We know how to make a line already in 3 space. So this just validates our technique anymore. We need a point. Right? That point in this case will be the point of tangency. We also need a directional vector. In this case will be our tangent vector. If we have those two things, then we can write our tangent line. Remember, lines are written two different ways: parametric equations or symmetric equations, not one equation in itself. All right, so let's find our point of tangency first. All right, they said at t equals 4. So we're going to plug a 4 into everything. 4 minus 3 is 1. Square root of 1 is 1. Plugging 4 into that, we got 2 over 3. And 4 into that, we're going to get 1 over 20. Right? Remember, this is not a point. That is a vector, because it's a vector function, right? It gives a vector, but it points at the point. So I can just change it to a point, keep the same numbers. Please do not leave that as a vector, two different things. So there's my point. Remember, the two things we need is a point and a tangent vector. So define my tangent vector. It's just the, we'll write that out, tangent vector. All right, so that's what we'll find now. Remember, the tangent vector, just like in Calc 1, if I want to find the tangent line or the slope, right, or the derivative, I take the derivative. So we're looking for r prime. All right. I still recommend going f of t. Okay, this is t minus 3 to the 1/2. All right, so that means f prime of t is 1/2. T minus 3 stays. This drops down, so it goes down to negative 1/2, and then it's the chain rule, so I multiply by 1. So I could just throw that in there. Actually, I'm not even going to really simplify that because I'm going to plug a value into it. So we'll leave it as is. G of t was 2 over, and I'm going to write it this way. We're going to do a chain rule here. That's to the first power. So it comes up, the power comes down, it's a 2 on top still, but it was a negative when it comes up, so it's a negative 2 over t minus 1 to the second power, because it would become a negative 2 times 1. Run a chain rule. If I confuse you, do it your way. I expect you to have that down at this point. That's not something I hope you're learning right now. If you're refreshing, that's something definitely that I expect you to know. So if you need to write out more, that's perfectly fine. To me, it doesn't bother me at all. H of t is the, and I'll write this how I was thinking about the other one. I was thinking about it like this. So now I could go, okay, the derivative then of h prime of t, that negative 1 comes down. T squared plus 4 stays, goes down to negative 2, and then I multiply by the chain rule, which is 2t in this case. That is going to be 2t over negative 2t over t squared plus 4, and that whole thing to the second power because I brought it down. Doesn't have to be negative anymore. All right, so that's what goes in each part there. And now I'm going to go ahead and just answer the question. They want r prime of 4. So we're just going to plug it into each component. If I plug in 4 here, 4 minus 3 is 1. 1 to any power is 1 times 1/2. We get a 1/2. All right, now plugging 4 here, we get a 3 on the bottom. 3 squared is 9. I get a negative 2 over 9. It's okay to have a weird number like that. Here, we plug in 4. We get 4 squared is 16 plus 4 is 20. 20 squared, maybe this one's going to get big, 400 is on the bottom. Plugging in 4 on top, we get negative 8 over 400. Now, negative 800, that'd be dividing both of them by 8, so we get negative 1 over 50. There we go. All right, so we just plugged all that in. So this contributes to our, what we need. We have a point and a vector. And then remember that they are component-based. Your point, so that's going to be 1 plus the 1/2 t. That's the vector. Then we get y. Scroll up. The point was 2/3 minus 2/9 t. It's like an mx plus b thing, right? Z is going to be 1 over 20 minus 1 over 50 t. Okay, so that's it. I feel like the hardest part, if anything, will be remembering how to make a tangent line in three space because we're having to reprogram our brain. Also, just be careful of your derivatives. I recommend writing it out like I did here, like I have been doing, and not trying to do it all in one line. All right, we have another example here. So it says find the equation of the tangent line in this one. So I'm going to write out the components. F of t is equal to negative e to the negative t sine of t. Let's go ahead and find that derivative. So f prime of t, it's a product rule. So we get e to the negative t, keep the sign, plus I leave the negative e to the negative t, take derivative of sine, which is cosine. I go ahead and factor that out, and there's a reason later. Sine of t minus cosine of t inside. Let's go ahead and do our g. Right, our g is e to the negative t cosine t. So g prime of t, it's a product rule. Right, we get negative e to the negative t cosine t. We don't touch that. And then we're going to get a e to the negative t. I'll leave that one alone. Derivative of sine t is negative, or of cosine t is negative sine t. We can factor out here negative e to the negative t, which means the insides just become positive. Right? And then we have one more, h of t, which is arc sine or inverse sine. Now, this is going to be a reminder, you could use a table. This is just for review here. This ends up being 1 over the square root of 1 minus t squared. You can memorize, you can put on your note card that you'll have. Like I said, I'm going to give a table. So you'll have a table to use. I will, if I can remember. If I don't remember, because sometimes I say things in these videos about posting something, and then I forget to post it once I get around to uploading and posting all these, I'll give you that table that will be on your desk, so you'll know what you're going to have as you walk into it. You won't have your table walking into it. You'll have a note card, but I will give you that table, a derivative and an integral table. So if it's not posted with this week of videos, please let me know through email to post them. Okay, so we have that. This now gives me r prime of t. So we have e to the negative t sine t minus cosine t I. I'm going to use a minus here. Minus e to the negative t. This would be an appropriate time to do that. Cosine t plus sine t j. And then the last thing is just a 1 over square root of 1 minus t squared k. Right, it says at time equals 0. It's going to be nice plugging in. So I'm going to find my vector. It's going to tell me which way the tangent line is going. The e to the negative t, if I plug in a 0, it just becomes a 1, so I just have to pay attention to the inside. Sine of 0 is 0. Negative cosine of 0 will be a negative 1. So I get a negative I. The second one, I'm going to have a negative from there. Cosine is a 1, sine is a 0, so we get negative j. And then the last thing, we're going to get 1, so plus k. I'm going to use these numbers. I prefer to see things like this. If you, it doesn't matter which one you use; they're equivalent. I prefer component form. This is my directional vector for my line. Okay, so we found a point. No, we haven't found a point. Let's do that now. So point of tangency. That's one we're going to use. Remember, we just pick whatever point we're looking at. That was t equals 0, and we plug it into our vector value function. So take a look. I'm going to zoom out. There's my original function. I can zoom back in, I think. Ooh, I got to finish this video soon. I'll grab a charger. R of 0, I plug that in. I get a sine of 0, so 0. Cosine of 0 is 1. E to the 0 is 1, so that one's a 1. Sine of 0 is 0 when we plug in a 0. So that gives a vector, but our point is going to be 0, 1, 0. Okay, remember we're looking at a line, so we have symmetric or parametric. We usually go with parametric. X equals, right? My point is 0 minus t. I'm using the vector and the point. So those two lines. Y is equal to 1 minus t. And z is equal to 0 plus t. We could rewrite this if we wanted, simplifying. Sure. X equals negative t. Y equals 1 minus t. And z equals t. So there is the equation of my tangent line. Feels very familiar. The only things that are a bit different is we're just dealing with a bunch of vectors instead of just a straight number. All right, I'm going to grab my charger. Forgive me. All right, so we have done a bunch of differentiation, as you can tell. It's not much different than what you did in Calc 1. The only difference now being that we're dealing with vectors, and we got to do it for any problem. We got to do it 3 times in each component. Surprise, integration is the exact same way. We just have to take the integral of each component. Let's do that for this first problem. So we take an integral of this vector. And we're not going to worry too much about what this means going backwards. What is the, like integration of a curve usually was area underneath. Maybe this means this in some weird way. We'll talk about this as we get closer into, as we get further into this chapter and semester. So let's take the integral of each part. So this is the integral of t to the third. All right, so that's 1/4 t to the fourth. I keep the component, minus 1/3 t to the third, plus, and then don't forget your component. See, I still do it. It's easy to do. 1/5 t to the fifth. Okay. Then they want us to run it from 0 to 1. That's our t's. So when I'm plugging these in, I actually like to plug it in 1 and 0 for each component. Meaning, like, I'm going to plug in 1 here, okay, and I get 1/4. Then I plug in 0, I get 0. I. Because I'm going to end up having to put the i's back together anyway. This is where I use a plus, and I don't leave that minus in between. Plugging in 1, I got a negative 1/3. Minus plugging in 0, I got a 0. J. Plus, plugging in 1, I got a 1/5. Plugging in 0, we get a 0. Okay. I would do that every time, even when they're not zeros. So this is 1/4 I minus 1/3 J plus 1/5 K. What does that mean in this context? We'll learn how to use these type of vectors and what they actually mean. There's a giant application at the end of the semester for this, so don't fret too much. We're just going to work on the mechanics of taking integrals of vector functions. All right, so I still, when things start getting complicated, that one was a nice, easy polynomial, so that's why we just left it. This one, I go back to the method of breaking down for each component. So the first thing we're going to do is the integral of t cosine t squared dt. Then we would do the integral of the other one, but let's focus on one at a time. This first one here is a u sub. I'm going to do a lot of review during this time of these integration techniques. I'll show you a bunch. All right, so we have that. I think about it this way: 1/2 du equals t dt, because I can take the t and the dt out. So this ends up being the integral of, okay, I need a 1/2. I'm going to pull that out. 1/2 integral of t's gone. T squared becomes a u, so I get cosine of u du. Let's figure that out. That's going to be sine, because derivative sine is cosine. I'm going to replace u with t squared, and then we get this plus c1. That was an I component. All right, let's do our j component. So I just put another bullet. You can put whatever you want there. We get the negative integral of t sine t. Now this one isn't the same because it didn't have the t squared, so we can't just do a u sub. This is going to require some integration by parts. And I hear some of you guys groaning. This one's not too bad. Okay, remember integration by parts, I need a du, and then I'll need a dv. And we work this formula going back, a formula, and we try to figure this out. And the whole point of this is I have two complicated functions, and I can't just take the integral one and the integral the other. Please don't try to do that. You're in Calc 3. Please don't try to do that. U subs like this for integration by parts is we want to put the function that will go away if I take the derivative as a u. So I'm going to put a t here, because if I put a t, this just becomes dt. And then I can put a sine t here, and I know that the integral, because I have dv, I'm going back, this becomes negative cosine t. All right, the formula for this thing is going to be negative, and I'm going to put it in brackets here, uv minus vdu. If you have trouble memorizing that, that'll probably be on that chart. I'll send the chart out, but that wouldn't be a bad note card thing. Okay, so uv, I got negative t cosine t minus the integral of, okay, and it's a minus inside, so I'm going to change it to positive cosine t dt. That is now a nice pretty integral that we can handle. This becomes t cosine t. And then we get, it's going to be a minus because that distributes to both of these, minus sine of t plus c2. That is my j component. Oh, I should have switched back to red. Sorry for those of you that will bother. I'm sorry. All right, so let's do the final component. That is the integral of t e to the t squared dt. This one is a nice pretty u sub, thankfully. U being t squared, so du is 2t dt. Let's go ahead and make that a 1/2 du equals t dt. I think that covers everything, so that will make this a we get a 1/2. Let's put that out front. Integral t dt gone, becomes 1/2 dt du. E to the u now, du. We get 1/2 e to the u as the answer, but I'm going to go ahead and replace u with t squared plus c3. And that's that component. So the answer to this thing here, I'm going to go ahead and shrink this so I have more room. Give me a sec. This integral, the answer for this ends up being, we have each component here. So I have 1/2 sine t squared. Then we got that constant, don't forget that, plus c1 I plus all of that t cosine t minus sine t plus c2 j plus, and then that final one we did 1/2 e to the t squared plus c3. This is the k component. So instead of writing it this way, because what we're going to eventually do is some problems where we're going to find these c's, what we do instead is we create a constant that just is a constant vector, because we could just put these three things together, c1i, c2j, c3k, and that could be its own vector. So what we do is we just write 1/2 sine t squared I plus t cosine t minus sine t j and then plus 1/2 e to the t squared k. And then we put plus c. If you want, you could put a vector there. I don't typically, I just put a plus c. It's just important to know that that's not a constant anymore. That's actually a vector. That vector being c1i plus c2j plus c3k. So just like Calc 2, bunch of integration, you're going to have to study your integration techniques. Again, I put those in week 1 if you need to go back and look at those. I'm trying to review and do a type of each one. These aren't going to go away. We do a bunch of integration in DE. So get them down. You'll have a better time getting through this if you're not struggling through every single integral that we have to do. And just forewarning, we are going to do a lot of integration. The back half of this course is almost nothing but. And we get into things double integrals, triple integrals. So definitely want to get our integration down. All right, let's do another example of integration of a vectored value function. Let's do each component. I think that is the smartest way. It's the easiest way to show your work. It'll be the best way for me to give you partial. So we have this function. This was mentioned earlier, but I don't know if you remember. This is the arctangent function. So that's what we get for that one. That one's just a good one to memorize. You would use a table that I'm providing. Then we have t over 1 minus 3t squared dt. And it looks like we're going to need to do some u subs here. U being the denominator. So du is equal to negative 6t dt. So that's negative 1 over 6 du t dt. That'll cover the t up top. All right, so going back to our integral, we have to introduce a negative 1/6, and then we get a 1 over u du, which is negative 1 over 6. The integral of 1 over u is ln of the absolute value of u. So ln of, and I'm going to change the u back, 1 minus 3t squared plus c2. We're going to drop these c's in a moment anyway when we write our answer. Right, the final integral will be the integral of 1 over the square root of 1 minus t squared. This has also come up in this section already. This is the arc sine of t plus c3. Use a table. I'm totally okay with that. I'm not going to ask you to memorize those. So the integral then is equal to the arc tangent of t I minus 1/6 ln absolute value of 1 minus 3t squared j. And then the last one was the arc sine function k. And then we just put a plus c. We know it's a vector. It's just important that you know. And the reason it's important to know will be the last couple of problems that we will do for this section. All right, these are going to be types of problems that you guys are going to do when you get into DiffyQ. If some of you guys are probably in both sections, I always have students that are in both. You would be crazy to do both in the summer. Kudos to you if you can make it. I believe you can. You just may not have a social life, which is fine, So let's look at another example. This example being R of t there. They say find R of t given that R prime of t is that function and R of 0 is that. This is called an IVP, an initial value problem. They give us a differential equation is what we see on the screen here, even though it's just a chilled out version with an initial condition. So what we're doing is if I want R of t, just back like in calculus, this means I just take the integral of R prime of t dt. So I'm going to throw all that stuff in there for I minus 5t squared j plus tk dt. Right? You just follow it like normal. 4ti, that's going to be minus 5 over 3t3, and then plus 1/2 t squared plus c. This is where we solve for the c. I know that I have this initial condition. I have an expression that I just found for r of t. So I'm going to plug in r of 0, plug that into the expression that I just found. So I get 0i minus, oh, I forgot my components on those. Don't be me. So moving those over, looks like I'll just do this. So we get j, don't do that, don't make this mistake, 1/2 t squared k plus c. There we go. Okay, so plugging in 0 there, I would have plus 0j plus 0k. So we actually gained nothing from that, plus c equals, and we just set it equal to what they had up there, I plus k, and we just solve for c. Well, there's nothing to solve for because those zeros go away, so c is I plus k. So that's going to be added back into our answer. This is going to get added. This is going to get added into that. So we just have to put a plus 1 for the I and the plus 1 for the k. So we write r of t, according to all this work, we get 4t, and I get the 1 from here, plus 1 I, minus, or let's go ahead, are we adding anything to j? We're not, so we'll keep the minus, 5 over 3tj. If you were going to add something to that, you'd want to do a plus and then do parentheses with minus inside. Then plus, and then we'd have 1/2 t squared. There's a 1k here, so I'm going to add plus 1, and that's my k. So there was my function. What an IVP does is it allows us to go backwards to get plus c's in our integration, but it allows us to solve for that plus c. That's all that's doing. We can extend this even further. We can start with our second derivative and work our way back twice, given that our IVP has enough initial conditions. As long as I have initial condition for the r prime and my function itself, then I can actually run integration through this. All right, so if I wanted to find r prime of t, this would be the integral of r double prime of t dt. So I'm just going to plug that in. We get 3e to the t. These look, I think, simple enough to not have to break them down. Minus secant squared t, j, minus, I'm going to go ahead and change this to negative 1/2, or positive 1/2, sorry, k, dt. All right, we could break it down, but I think these are fine enough. We want to take the integral of that. Integral of 3e to the t is 3e to the t. This is a tangent, because the derivative of tangent is secant squared. And then we get this, where you go up by 1 and divide by our new one. So I go up by 1 at 3/2, I get minus 2/3, because that's dividing by the new one, to the 3/2 power, k, plus c. Now, I use this initial condition, r prime of 0 is going to be here. So I plug in 0 to my function that's on the screen. I get 3i. Tangent of 0, that's sine over cosine if you want to think about that way, it's a 0. So 0j plus, that's a 0k, plus c, and it's going to be I minus k. Well, the only thing to happen here is to minus 3i over, so that lends me to negative 2i minus k. So now I know that r prime of t is equal to, okay, and I get to add these into each part. 3e to the t, I have a negative 2 that I'm going to put in with the I. Right, then I don't have any j's, so I'm just going to write that one. I forgot the t, j. And then this one, that minus is what I was talking about earlier in this problem. Plus, I put minus 2/3 t to the 3/2 minus 1 k. All right, now I have that function. If I want to get down to my original function, I take the derivative of, the integral of its derivative. So all this goes in here. I think, what was that? A 3, yeah, 3 over 2. Minus 1, k, dt. And then we just take the integral of this stuff. Okay, so the 3e to the t just becomes 3e to the t minus 2t I. The tangent, I'm not going to go too in depth with that tangent, but the tangent just becomes a minus ln of a cosine of t. You can use a table for this, or you can think of tangent sine over cosine with u sub. So I would recommend the u sub. Check that out. It does work. You get the same exact answer. A table may look slightly different. They may take that -1 and put it up in the power of that cosine and use a log rule. And then 1 over cosine is secant. So you may get a secant from that, right? And then this crazy mess, after working that out, I'm just going to go ahead and give it to you. It's -4 over 15 t to the 5 halves minus t. Right? And we get that. And now we have another plus c. We had one more initial condition up there at the top. It was r of 0. So let's go ahead and plug that into the function we have so far. I think we get 0 in that term. We get a 3i. If I plug 0 into cosine, I get 1 ln and 1 is 0. So I get 0j. Plugging 0 into the third term, I get 0k plus c. And then the condition they gave was 3i plus j minus k. That's from the top, the initial condition they gave us. I solve for c. Solving for c just means I minus 3i, which means I get j minus k. Now we have our answer. R prime of t is equal to, and we just plug the j and the k into those spots. So we get 3et minus 2ti. Then we had to add a plus j in, so this is going to be a plus negative ln. It's still silly. Let's throw the 1 up front, actually. Let's just do that. 1 minus ln. That looks much better. Cosine t j. And then we're going to put a minus 1 in the k component. 4 over 15 t to the 5 over 2 minus t minus 1 k. All right, so there's our original function. Just back from Calc, Calc 2, you may have done these problems. I know some instructors do them, some don't. But these are going to be a common problem that you will do in DE. It's actually most of DE is this IVP idea.